Swayam Prabha. Digital India. Educated India.
In the last class, we have talked about some of the electrical properties of materials. We have talked about resistance, we have talked about resistivity, we have talked about conductivity of metals, of polymers and of ceramics. Now, we will talk about another very important electrical property of the material, and that is the dielectric property of the material. It is just the reverse side of the conductivity. That means, if a material is not conductive, then every possibility that it is a dielectric material, or so to say, very commonly say that it is an insulating material. But what is this concept of dielectricity? That we will see, and we will see that how it is applied to the capacitors. Finally, we will also do a small material selection again exercise for microchip heat sink using the Ashby approach. So, these are the three things which is our learning goal in today's lecture. Now, about first the dielectric behavior concept. Dielectric is generally, it is a material which is used to separate two charged bodies. So, for a material to be a good dielectric, it must be an electrical insulator. Now, as a result of the dipole interactions with electric fields, dielectric materials are actually utilized in capacitors to store electric energy. You must have seen that very common example of a parallel plate capacitor, where we have two conductive plates and you have the dielectric material in between. And what is it? We call it, when we apply high voltage to the system, we call this to be a parallel plate capacitor, which is an example of this type of a parallel plate capacitor dielectric system. So, when a voltage V is applied, for example, that is what we have shown here, on across a capacitor, one plate becomes positively charged plus Q, and the other becomes negatively charged, because the electron is not able to freely conduct between the two. So, the plates would become charged, and because in between you have the insulating medium. Okay. So, that creates this separation of charges, and which remains stationary between the two. And the capacitance C is described by this very common equation, which is C equals to Q over V, where C is the capacitance, which is coulomb per volt, or farad is generally the unit of capacitance. Of course, the type of capacitors that you will usually see is 10 to the power minus 3 farad, or so to say microfarad. That is the more common types of capacitors you will usually see. Now, while talking about these dielectrics, we have to also start our story from a little behind. We have to start our story from the polarization. For every electric dipole, there is a dipole means whenever you have a negative charge and a positive charge like this, okay, there is a separation distance between a positive and a negative electric charge, right. For any dipole, two polar bipolar system with negative and positive charge, there is a separation distance T. And so, you know that the force that works between these two is called the Coulomb force, right, Coulomb force, and this also follows the inverse square law. So, it is actually proportional to the force is proportional to the charge, and then it is inversely proportional to the square of the distance between the two poles. Now, the force that works like this, that is separated by a distance d will actually create a dipole moment P, and this dipole moment can be actually expressed in terms of the magnitude of the dipole charge q times the separation between the charges d. So, this is the dipole moment, and if there is a electric field, a force or a torque acts as an electric dipole to orient it with the applied field, and this process of dipole alignment is called polarization. For example, you have a charge q minus q, and they are sort of having the forces interacting, and they are subjected to an external force. So, this external force will actually try to electric field type of a force will actually reorient them. So, this will reorient them with the direction of the external force, and this activity is called polarization. Now, there are several types of polarization. It's like alignment of permanent or induced atomic or molecular dipole moments with an externally applied electric field. The three types of polarization which are very common are: one is electronic polarization. As the name suggests, this is due to the displacement of the center of the electron cloud around the nucleus under the applied field. And then there is ionic polarization, Pi. This occurs in ionic material as the applied electric field displaces the cations and anions in opposite directions, resulting in a net dipole moment. So, that is the ionic polarization. And then there is a third type of polarization which is known as orientation polarization. This I actually, when I have talked about the smart materials, I told you that this only happens in some materials which are having permanent dipole moments, okay, like this AbO3 crystals I told you that which has permanent dipole moments in it. The rotation of the permanent moment in the direction of the applied field causes the polarization. So, once again, the electronic polarization Pe, which is due to the electron cloud displacement. Ionic polarization is occurs in ionic material, like all ceramic materials which are basically having ionic bonds, and then electric field displaces the cations and anions in opposite direction. So, you will see this, and orientation polarization only in certain very specific group of we call non-centrosymmetric crystals, like these AbO3 type of systems, where you are going to see the orientation polarization. Now, the total polarization P is then can be expressed as a summation of the electronic polarization, ionic polarization, and orientation polarization. So, here in the figure we have explained the same thing to you, that under no field this is the system, but as you apply the electric field, then the electron cloud shifts itself, and that is the electronic polarization. In the ionic polarization, you can see that this happens with the ionic system itself, that they reorient themselves, as you can see it here. And for the orientation polarization, where you have the randomly dipoles, aligned dipoles, the moment you apply the field, all of them approximately aligns themselves towards this direction of the applied field. That is the orientation polarization. When vacuum is present, so now we are talking about quantification of the dielectric field. When vacuum is present, then surface charge density or dielectric displacement, we will call it D, is actually proportional to the electric field. Okay. So, D, if there is a vacuum here, then D is epsilon 0 times E, where epsilon 0 is the permittivity of the vacuum, which is in terms of farad, it is of course, as I told you, that it is even smaller than microfarads, very very small, something close to picofarads. It is 8.85 into 10 to the power minus 12 farad per meter. Any other material an analogous expression exists for dielectric case, which is d equals to epsilon e, where epsilon is the permittivity of the dielectric medium. So, the surface charge density is possible due to two things. One is due to the applied electric field and another is due to the polarization. So, hence d is epsilon 0 e plus polarization. So, P is here the polarization or the increase in charge density above that for a vacuum because of the presence of the dielectric medium that is there. And as you can see that this is what is also explained in this particular figure, that the moment you apply this voltage, there is a net negative charge at the surface, there is a net positive charge at the other surface, and accordingly the dielectric medium orients and there is a region of no net charge which will be there. Actually, as you increase the voltage, this starts to penetrate actually, and as it penetrates more and more, there could be a dielectric breakdown, a dielectric sharp breakdown. That means its capacity of holding the charge will suddenly break, and that will be a collapse of the insulator. Now, the capacitance depends on the permittivity of the material. That means that it depends on the plate area of the plate. Of course, when you will calculate the area of the plate, you have to find out what is the common area of the plate. Suppose this plate is slightly bigger, in that case still the overlapping area will be this much with the plate in the bottom. So, that is the common area, and then epsilon 0, that is permittivity of vacuum, and divided by the separation distance L between the two, which is the separation distance between the two. The same thing is also true for the any other dielectric medium, where C is epsilon A over L, where epsilon is the permittivity of the dielectric medium, and that is epsilon 0 times epsilon r. That is epsilon 0 is the vacuum permittivity, and epsilon r is the relative permittivity. Epsilon r is always greater than 1. Then polarization is the orientation of the permanent or induced dipoles under externally applied electric field. I already told you, and it results in increase in the surface charge density d, which is measured in coulomb per meter square. So, thus there is increase in charge storing capacity by insertion of the dielectric medium, okay, because in comparison to the vacuum it has epsilon r which is greater than unity. So, there will be more charges that you will be able to store if you insert a dielectric medium in the system. This dielectric constant, it has a frequency dependence. For example, when it is subjected to polarization by an alternating electric field, then with each direction reversal the dipoles will reorient itself with the field. So, this is a case where dipole orientations for direct polarity, and then as you change, then this negative will become positive, this positive will become negative. So, a dipole reversal is happening. For each polarization type, some minimum reorientation time however exists. It cannot happen very fast. Okay. So, it all depends on the ease with which the particular dipoles will realign, and this is actually how fast it can do is governed by its relaxation frequency, which is taken as the reciprocal of this minimum reorientation time of the dipole. So, what happens then if I apply an electric field which exceeds its relaxation frequency? Of course, dipole will not be able to keep shifting orientation of the direction. Thus, there will be no contribution to the dielectric constant, and polarization mechanism ceases to function. There is an abrupt drop in the dielectric constant of the medium. So, you can see here that the dielectric constant with respect to frequency, as you can see here, that I am increasing the frequency gradually from like kilohertz to megahertz, gigahertz level onwards, and the dielectric constant initially is stable, but then it actually fails. So, it is coming down, okay, and then it is remaining stable, and then it further comes down finally. So, the point is, first what is going to fail is the orientation polarization. Second, it's the ionic polarization, and finally, if it is very fast electric field, then it's the electronic polarization which is going to fail, and it will not be able to follow, and there will be a sharp breakdown of the dielectric constant. So this is, you will see a dielectric loss in the system. Now, of course, a low dielectric loss is what is desired at the frequency of utilization. So, for example, when we actually transfer power, a high voltage power from position A to position B, this property is very important, that whatever is the line frequency, with respect to that line frequency, the relaxation frequency should be such that particularly the orientation loss is what you expect, and that should not happen. Okay, so that is how you have to choose the material. So when very high electric field, so the other point is, I told you that if you apply the voltage, a very high voltage, then there is a sudden excitation of large number of free electrons to conduction band, and thus high current will lead to either localized melting or burning or vaporization, and that is called the dielectric breakdown, which represents the dielectric strength. So, you have to think of two things, one is the frequency and another is the dielectric strength. So, for many materials like common insulating materials, like suppose titanate ceramics, it is dielectric constant is 15 to 10,000 at 1 megahertz level, and dielectric strength is about 50 to 300 voltage per mil, where 1 mil is 0.001 inch. It is still the kind of a PS unit which is important here, which is used here. For mica, which is also used as a very good dielectric material, it is 5.4 to 8.7, and that is the dielectric constant. Strength is 1000 to 2000. Then there are some natural materials, steelite, soda, etc., and porcelain, which is very commonly used, is about 6, and dielectric strength is between 40 to 400. Fused silica, it is about 3.8, it is about 250 volt per mil is the dielectric strength. How about the polymers? Well, some polymers show excellent dielectric strength, like phenol formaldehyde 4.8, but the strength is 300 to 400, quite comparable to porcelain. Nylon is about 400. Okay. So, what is low for them is generally the dielectric constant is low for them, but they have a good value of the PTFE, for example, polytetrafluoroethylene, they have a good value of the dielectric strength. Now, these are the average values of magnitude, but it also depends on the specimen thickness, the geometry, rate and duration of the electric field, all these things comes into picture, but this is like the average value that you will find in these materials. I am going to talk about one exercise that we have said that this will be related to the material selection for the micro chips heat sink. Okay. So, let us see that how we can do it, and there is an exercise towards another application of SB chart for a non-mechanical property set. It is a very interesting one. You must have seen the microchips, right? Any computer system, miniaturized electronics is full of such microchips. Now, these microchips is a series of many integrated circuits which are there, and even though they consume milliwatts of power, but it is dissipated in a very tiny volume. As a result, the power is low, but power density is very high. The Pentium chip of today, for example, that reaches a temperature of 85 degrees centigrade. So, which means you have to cool it constantly, otherwise the chip will not work. Multiple chip modules, MCMs pack as many as 130 chips onto a single substrate, and imagine each one of them is reaching a temperature level of 85 degrees centigrade. So, you have to have a lot of cooling arrangement, and this is where the heat sink comes into picture. So, as you can see here that suppose this is the chips here, okay, and then there is a substrate, there are connecting pins with which it is in one side it is fixed with the circuits and towards the computer. The back side of it you have the heat sink and the cooling fans in the back side of the heat sink. Now, when we have to select a material here, the heating is kept under control by attaching the chip to this heat sink, which ensures a good thermal contact between the chip and the sink. So, the heat sink has now become a critical component limiting the further development of the electronics. If your heat sink is, if you can make it more efficient, then you can pack more electronic circuits in a smaller area. So, the choice of material for the heat sink is very important. Now, what is the contradiction here? That it must insulate electrically but conduct heat as much as possible. That means from the chips it should only conduct the heat but not the electricity. That is what we will see is very important. So, select a material for a heat sink that must insulate electrically but conduct heat as much as possible. In other words, you have to maximize the thermal conductivity but minimize the electrical conductivity, or at least say that the electrical conductivity is something less than something like the resistivity is greater than 10 to the power 18 micro ohm per centimeter. So, also the temperature it has to withstand is something like 100 degrees centigrade. So, with this type of conditions here we can directly actually use the ASB charts. So, we need a plot of electrical resistivity in our x axis and the thermal conductivity in our y axis. So, what we want to do here is that we want to maximize the thermal conductivity and we also want to maximize the electrical resistivity, because that means it will be more like an insulating material. So, if you choose certain like a border like 10 to the power 18 micron centimeter, then it is the top part of the curve, this is where we are interested in, where you get high value of thermal conductivity and high value of electrical resistivity. Just the opposite is this region where you get low value of electrical conductivity and low value of thermal conductivity. So, low value of electrical resistivity and low value of thermal conductivity. So, it is the top part we are looking at, and here what are the possibilities for us? Aluminum nitride you will see, technical ceramics like Al2O3, Si3N4, these are the things that you will see in the top part. Now, if you further expand this, what you will see is that there are three materials which will come to your focus. One is aluminum nitride, then the silicon nitride and aluminum oxide. So, these are the materials which are which gives you a high this electrical conductivity, or so to say the resistivity wise you will get a better resistivity, that is 10 to the power 18, but the thermal conductivity, so which is greater than 20 watt per meter Kelvin. So, with that we can get such materials for us, and if you further magnify you will also see there are some materials which also comes inside like diamond for example, okay, which is slightly better in terms of the thermal conductivity, but not in terms of electrical resistivity. Of course, diamond is very expensive. Then the beryllium compounds are also there, beryllia, but I told you that beryllia is toxic. Magnesium oxide is also there, that is also generally not used, as that is also toxic. Thus, we can see that the safe bet is actually the alumina. So, alumina or silicon nitride, either of them is the safe bet for us. So, this is how we can select the material. Now, in the next lecture we will learn about the magnetic properties of a system. Thank you.